In the example 2 that we worked through, where we saw the two samples and then the sample means, the distribution of the sample means, that was called the sampling distribution, and that actually leads us to this nice theorem. Okay, again, a little technical. We'll walk through it and then make sense of it in a minute here. Okay, so the central limit theorem, huge cornerstone of statistics and statistical theory, as you can tell. But the idea is that you have some observations that, again, are random variables because you don't maybe know their outcome at the beginning. But they're going to be IID, so that's, again, independent and identically distributed random variables. And we have finite mean and standard deviation, so just that one is satisfied trivially for us because we're always going to be working with finite or concrete values. But then for a sufficiently large sample size, now this language is problematic at best, but in most cases, sufficiently large means that our sample size is greater than 30. Okay, and then we say that the sample means, okay, so this is the sample means. If we look at many, many sample means, so this is the 1 through 50 repetitions of the experiment, right? If we look at creating a histogram of those sample means, that distribution should be approximately normal, where we have the mean of that normal distribution being the population mean, and we have the standard deviation as a sigma over root n. This is actually called the standard error, okay? So you might recall that when you did in the data analysis tool pack, and you did summary statistics, it gave you standard deviation and standard error. Standard error is just standard deviation over root n. Okay, and then so we have approximately normal, and in fact we would have that it is normal if we're sampling from a normal distribution. Okay, so in order to do this, there's a few things that we have to verify. First, we have to verify that the xi's, our observations, are IID, so we're sampling them or we're getting them independently and they're identically distributed. Really, if you have an SRS, that satisfies this piece. Okay, so that's one way to check it. If you have an SRS, you're going to have IID. And then second, we need to verify we have finite mean and standard deviation. Okay, so are they a number? Okay, and then lastly, 3, we either need n greater than 30, or technically this last one, or we need normally distributed. Okay, so before we can use the conclusion of the CLT, we need to go through these 3 checks. Okay, but the question is, okay, great, we have this theorem. How do we use it? Okay, glad you asked, because we're going to do 2 examples. Okay, so context, let you pause the video, read it through. Okay, so we're looking at weight, which is a normally distributed characteristic, and we want to find the probability that a randomly selected US man has a weight of greater than 180 pounds. So this one actually doesn't use a CLT, because if we have randomly x is the random variable representing the weight of a US man, right? A randomly selected US man, right? That's just x, right? So I'm looking for P of x is greater than 180. Okay, well that's simple, right? This is chapter 11 stuff. This is 1 minus norm.dist of 180, and then the mean is 70 and standard deviation is 30, and then true. Okay, and we can get a number. Okay, not so concerned about that. What I am interested in is part B, because now the problem changes and I'm no longer looking at a US man, right? I'm looking at the probability that 20 randomly selected US men. So that I get a group of 20, and what is the chance that their mean weight is greater than 180? So this changes, okay? I'm looking for the probability that any mean of size 20 is greater than 180. Okay, that's what this exercise is saying. So I'm looking at the sampling distribution because I'm looking at all samples of size 20 and the chance that that any given sample is greater than 180. Okay, so now to calculate this, I'm going to calculate it similarly. I'm still going to use according to the CLT now, right? According to the CLT, the samples of size 20 would approximately, and actually that will follow a normal distribution since this is normal. It's going to follow a normal distribution with mean mu, which is 170. But then the standard deviation here is going to be 30 divided by the square root of n, the square root of our sample size, which is 20. Okay? So if you want to get a value, you can for that, but what I'm going to do is go to Excel and type in 1 minus norm dot dist 180, 170, and then when it comes to standard deviation, I'm going to actually type in 30 divided by square root is just squirt in Excel, square root of 20. And again, you can do that on your calculator if you wish. 30 divided by square root of 20, that is, and then true. Okay, so let's go to Excel and do that. All right, so I'm in Excel and I'm just going to click a random cell and type what I said in 1 minus norm.dist of 180, comma, 170, comma, standard deviation, that was the 30 divided by square root of 20, and then do true, and boom, I have my answer of about 6%, well, almost 7, okay? So again, the only thing that really changed, because I'm looking at the sampling distribution, is the standard deviation. Okay, remember sampling distribution is still normal if we're sampling from a normal, it's just less spread out, so that's why the standard deviation needs to change to the standard error. Okay, and I'm just going to record that answer. Okay, about 6.8%. Okay, so we've answered that question. First one, be careful, you don't always need to use the CLT. You can just use our knowledge of the normal distribution. Okay, next example. Okay, I want you to read it through and answer part A on your own. Resume the video when you're ready to discuss or listen to the answer to part A. Okay, to apply the CLT, right, you have to do the checks. So let's do the checks. First, are the observations, the soda cans in this case, are they IID? So are they made independently and from the same distribution, from the same manufacturer? Yep. Okay, so that one is satisfied. Are mu and sigma finite? Is the population standard deviation and population mean a finite number? Yep, they're each finite numbers. 12 and 0.11 respectively. Okay, and then do we have either the cans following a normal distribution or the sample size being greater than 30? We have the sample size is 36, so that's satisfied. Okay, so I'm going to say yes, CLT applies. Okay, part B. Determine the probability. Okay, now I just have to, I see the probability, I have to write the statement. So P of something. That the mean amount of soda in the samples, so that would be that the mean of the 36 samples, okay, and looking at all possible arrangements of those, okay, is more than 12 ounces. And I actually made a typo here. This should be 12.05. Okay, so probability that the mean amount of the sodas in the samples is more than 12.05 ounces. Okay, so now to do this, again, this is the sampling distribution, so the CLT has to be used, and I said the CLT applies. So what I'm going to do here to calculate this is I'm going to do 1 minus norm dot dist of the value of interest, so 12.05, comma, 12, comma, the mean, which is the standard deviation, so 0.11, divide by square root of 36, or just 6. And then, oops, I'm running out of room, true, and I'll get an answer. Okay, so let's hop over to Excel and do this calculation. And in Excel, we do 1 minus norm.dist of 12.05, comma 12, comma 0.11 divided by square root of 36, and then true. There we go. So 0.3%. 0.003. Okay. So unlikely. Okay. And then part C, does the data suggest that the cans are filled with amount greater than 12 ounces, and then uses 5% significance level? This one I included just as a challenge question, so I want you to respond to that. Remember that early on we talked about making decisions about like reject or fail to reject based on comparing a p-value to an alpha value. So I'm going to let you draw your own conclusions there. Okay, the main point here was to do part B, where we looked at the mean amount of soda being bigger than 0.25 ounces for a sample of size 36. Okay, and we verified the CLT applies here, so we're in ship shape. So I guess big thing with the central limit theorem, know that we're looking at the distribution of a statistic. In this case, the version that we worked, or the statistic that we worked with here was a sample mean. We will see one soon with a different statistic in mind.